Hi, I'm going to derive I'm going to basically derive cause and effect for conservation of momentum, which is m1 v1 equals m2 v2, from f equals ma. So let's get started. So this is f. Oops, I guess that needs some work. Oh, good. Well, I'll be right back. Oh no. Yeah. Uh-oh, someone's giving me a call. Sorry. Hello? Yes? 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 Okay. Okay, yeah, he left. Yeah, bye. Oh! Okay, bye. Alright. Okay, so we got F equals ma, right, from Newton's second law, and this is the cause, and this is the effect. We can act or apply a cause or force, and it causes more acceleration or results or produces more or less acceleration. So what Newton did is that he basically was isolated because there's a bubonic plague going on, and he was not bubonic plague, but it was a black plague, and he was stuck in Cambridge, and he had nothing to do, and he didn't learn, and all he did was think and create. He stopped learning, and this is how brilliant this is. So we can basically say that A is a change of velocity over a change of time, right? From the graphs we learned about position versus velocity, and how the slope is velocity, and then you can do velocity relative to time to find acceleration. So that we can substitute this for delta v, change in v, over delta t, change in t, or if you're in calculus, like this, which is same as A, and later on, this is the way Newton wrote it, but sometimes mass is not constant. That's the problem, right? Sometimes acceleration is constant. But usually, so what we could do is that we could find the impulse, which is equal to the force, and which is equal to the change of force of change time equal to m change of v, right? So sometimes these mass isn't constant all the time, and we could change the momentum. Because momentum is mv from what we've learned before, and remember what force is. Force is mass times the speed, right? Or mass times the acceleration. Sorry about that. So momentum is basically what can happen, not the force that's actually applied, but the momentum, which is sort of like the slope of that. These mass is constant in the situation. And now we can change this to f change of t is equal to m change of mv, right? And now what we have is that we can say for change of mv is equal to large change in time. It could be a small force and a large change in time, or a large force or a small change in time, right? So this is how we get the impulse. And now we can move on to find the equation from this. Right? Okay. So now let's say we have a ramp in which we did the experiment, and we had carts, right? And let's say this is M1, this is M2. and they're traveling at the rate of v2 and v1, or either way, right? So, what we can do is that we could basically find how we measure time. So we measure time, we can measure time from when this part goes from this place to this place. It's hard to find velocity, we know the mass. But what we do know is that velocity is equal to position relative to time. So you can write m1 over x over v times v1, which we're calculating, is over m2 v2 is equal to m1 x over 1 over t1 over m2 x over 2 over t2. And guess what we can get? We know that t1 is equal to t2 in this time because we know that the velocity is the same here, knowing that the velocity is the same, and knowing that the mass is the same. We can say time is the same, and we can get this out. And now we have a nice way of getting m1 x1 over m2 x2. Now, if we know if this is around equal, and Mother Nature is nice to us, we can get the approximation of 1, because we know this. So, yeah, this is how we avoid measuring time, which is awesome. Thanks.